So today we'll have another installment of the segment, very detailed answers to questions nobody asked. So I hope this is not going to be too weird. So we're going to talk about data structures for decentralized exchanges. So it's not so much of a Cartesi infrastructure talk, naturally. It's more of a DApp discussion. So it's not very usual because, DApps is not what most people in the audience here do. Most people are concerned with the infrastructure itself. But, the DEXs are a very important type of the app. So I figured I was going to talk a bit about it. So I'm going to first explain why I think the DEXs are so important, talk a bit about how they are usually implemented in the centralized world, and then I'll explain why the standard implementation is not ideal and give some suggestion for possible alternative. Okay, so why the access? So first of all, they're very, very, not only the DEXs, but the exchanges in general, they're very central to crypto. For two reasons. First, because it's something people want to do. It's something that was in the original vision of Ethereum, for example, is to have the ability to code options and complex financial instruments on smart contracts. And it's also very important because the way blockchains like Ethereum are organized, there is this fight over block space. And since crypto finance won this bidding, it basically killed the other fields a little bit. So games went to layer 2 or outside chains. So they're very central to crypto because they're important, but also because they eliminated the competitors through bidding wars. Also, it's important to see that exchanges can survive in the current tech. So although we definitely expect scaling to give a big jump in the near future with improvements on data availability on L1 and the work we are doing at Cartesi and other projects on L2, we believe that the scalability of decentralized technology is going to give a big leap forward. But it's just not there yet. Even if you use L2, it's still quite expensive to send a transaction, say 10 cents. And that's too much for several kinds of games people could come up with. But for exchanges, that's fine. People would be happy to pay 10 cents to make tradings, for example, in their usual trading platform. So it works with the tech we have. And it's something, so decentralized exchange is something that the better you scale, the more computational power you have, the best it is for the users, very directly. So I'm going to enter into that a little bit more, but you can think that if you have a exchange that is very slow to process data, like it used to be when the stock exchange of countries were run on paper, first of all, it has excluded a lot of people from participating. So ordinary people could not go to the exchange because, they wouldn't have enough paper processing power to handle all the individuals. So as soon as it became digital, people could participate. And then from there on, the digital part became faster and faster. So you had you could already put bots and automatized things on top of it. So the more scalability you give to the exchange, the best it is for the system, the more utility it gives to the community. And another advantage of DEX, so this is why DEX is so important for Cartesi specifically, because we, I think, give the best scaling properties out there. And also, we gave this lot of scalability in exchange for a bit of impediment in composability, but the DEXs don't need so much composability. It's nice to be able to put some strange tokens inside the exchange, but that's about it. It's something you can easily do in Cartesi. It's not something that you need to compose a lot with other DApps. Okay, so let's talk about the usual way people think about exchanges. So if you go, for example, to interactive brokers or some other non-decentralized exchange, it's going to look like this. You have people making bids, say to buy Ethereum using BUSD. So here's the price in BUSD people are bidding on, and here's the volume. So this, let's say it's 4, 5 something, and this is 20. So people are buying 20 Ether at the price of 450 something, 4,500 BUSD, and this accumulates. So the total area below this curve is the total volume of bids, although the ones that are very low here, they are not very important because it's like people saying they would buy Ether if it was very cheap. But it's, people who are actually trying to sell it here, they're asking for much more. So let's see the other side of the coin. So here people are asking they're giving Ether in return for BUSD, and they are asking for this much, and they are offering this much Ether. So you see that there is no intersection, because if there was an intersection, if someone wanted to buy at the same price someone wanted to sell, there would be a match. So there is a line here that separates bids from asks, and this is the price, what people usually call the price. Of course, it could be that the bids stop here and the asks start here, so there's a bit of a gap, and that gap is known as the spread. Okay, but this is this usual stuff. Usually everyone will say, I want to make an ask or a bid. They'll say who they are, what price they want to either buy or sell, and the quantity they are putting in or asking to in return. These are always disjoint, as I said, and if someone introduces a new bid right here in the middle, like I want to buy at this price. So person puts a price here and they want to buy. So you can take everyone here that wanted to sell and match those, and either this is gonna, eat just a little bit of the selling orders and be fulfilled, so the price would have moved here, or maybe there are not enough selling orders and it's gonna buy all this and still create another bid here. So it could be that the new order is fully fulfilled and still there is something remaining, or it's fully fulfilled and there's nothing remaining. But anyway, you can do the same with asks here and eat through the bids, but they will always be disjoint. Okay, so how this is usually implemented, you put, for example, all the bids in an array, and then when a new, these are asks. So when a new bid arrives, you just loop through the array, matching, match, match, match. You see here, for example, there was a bid at this value for this volume here. Just match this, match this, match this, and there is, okay, still some ask here remaining. So this is good. It's how 99.9% of the people do it, I think. And you can't actually put it in an array, because you see it had to be ordered for us to just loop like this. So if it has to be ordered and someone introduces a new ask here in the middle, you don't want to push the whole array to the right and insert another element here, right? You want something that is more efficient to insert things. So don't actually use arrays, use B+trees. I'm going to talk about B+trees later. So you just, as I said, just loop and find all the matches. What are the advantages and disadvantages of this approach? First of all, it's very simple. And there are several very optimized implementations of this. Just, have a loop, so you can use memory locality, you can use several different tricks in the book to make this very fast. Another advantage, it's very synchronous. So let's go back to this slide. As soon as this bid is put, you match all of them and you distribute the money to people that were involved. So if there were 100 people here making up this ask, this volume at this price, you give them all the money they asked for, and you get the assets and you give to the bidder. So all of that is matched instantaneously and synchronously. This is an advantage. The problems that come is, okay, it scales linearly with the number of matches you're going to do. So, imagine that someone makes a bid very high up here, and there are lots and lots of asks building this volume. You have to look through all that. So this harms scalability. And especially in decentralized scenarios where we are open to anyone doing any crazy stuff, there is kind of an attack, which is not really an attack in the sense that you make money out of it, but it's a griefing attack where you make the system slow and inefficient by attacking it, where you make tons of one-way. So wave, people don't know, it's just the small quantity of ether. It's a 10 to the minus 18 ether. So you can make quadrillions of these asks with 1 cent of a dollar. Of course, if you can give the data availability of all that. But if we don't want to enter into the details, it's possible to make tiny, tiny, tiny orders to different accounts. And people would have to look through all that to clear the book. So it kind of creates a barrier, a computational barrier for people to cross a certain price. And it's very hard to tell if this can be used or not to make money, if you can delay the computation or I don't know. And as I said, the more computationally efficient your system is, the best for the utility of the overall community. There is this problem here, especially this one, is so severe that people had to come up with alternatives to make things on Ethereum. So the most well-known alternative of a decentralized exchange is Uniswap. So Uniswap does not create an order book. Everything I said until now does not apply to them. So they don't have also this big storage necessity, like Bob is selling this much for this price, Alice is buying this much. So they don't have to store all that. All they store is 3 numbers, like this contract here for this pair, Ether BUSD. It has 500 Ether, it has 1 million BUSD, and I want to keep that product of Ether times USD. So actually only 2 numbers need to be stored. So when people buy and sell, there is a formula, magic simple formula, to calculate the price that people are going to pay. And this formula is such that the product of the volume of Ether and the volume of BUSD is kept constant. So because of this simple formula, the matching always takes constant time. It's not linear in any number of bids. There's not even a number of bids stored. As an additional advantage, the system has a built-in market maker. So a market maker, if people don't know, is someone who comes here and sees, that, for example, there's a big spread here. Let's put some orders here to fill the gap. I know that the price is here. If there is a gap here, I should come and fill the gap. Also, there is a way for people who are not interested in trading so much. They just have spare money to invest, they can stake the money there, and they will make a little fee out of the people who are actually trading. So there is a built-in staking system. And also, when you stake, you get a liquidity token that you can, send elsewhere and, land it in a crazy platform. So it's actually very interesting in terms of composability as well. So this looks like the perfect world, right? You have something that's simple, that's efficient, provides a market maker, and staking is composable. The problem with this, and this I cannot stress this enough. Yes, Coaching?
Yeah, what is this liquidity token?
So when you want to provide liquidity, let's say there's a 1,000 Ether and 2 million BUSD inside the contract. And you say, actually, I don't want to buy anything. I just want to double these amounts, right? So I want to give more Ether and more BUSD. So I'm going to increase the volume of the system, which is good for liquidity. It also reduces the price slippage. Like when someone buys, the price doesn't change so much. So you add this, and you get some liquidity tokens. So let's say you give $500, 500 Ether, and 1 million BUSD, and you get some liquidity tokens that in return will give you this product of these volumes. You don't know if you're going to receive in the end the same proportion of Ether and BUSD, but you're going to receive some combination of them that when you multiply their quantities, you get the same product as you had before. And this is registered as a token that you can later burn and get your quantity back. Maybe at a different proportion, but this liquidity token is something you can trade elsewhere. And it gets fees. That's what Philippe is saying. So when you put the money in, you get this liquidity token. But every time someone trades, it's not that actually the constant product is fixed, but it reduces by a tiny little bit. And by this fact, you're giving everyone who provided liquidity a little bit of a fee, like an implicit fee. Their shares increase in value.
I see. So for that specific pair, you have this liquidity token, and you can trade that. So is it possible to be like a different, like a swap pair or something for this liquidity token and I don't know, Ether again or something?
Yeah, you could make another Uniswap where you put liquidities, but Uniswap usually centralizes the creation of new contracts. But if they didn't, you could create another smart contract that acts like Uniswap, and on one side it has a liquidity token of another Uniswap thing.
Okay.
And there is an implicit price in every Uniswap pair. So there is a price that you can look by the constants that it stores. And if this price is off, like in the real world, the Ether is worth 2,000, and in the contract it's worth 1,900, someone can make some gain by trading there. And this arbitrage, sometimes it's better than the fee, sometimes it's worse than the fee you pay. So it has to be well thought, but it works. So if you look at Uniswap, usually the price represents indeed the price in centralized exchanges.
Okay, thank you.
But okay, I cannot stress enough the problem that systems like this have, like Uniswap and Curve. It's very bad, very, very bad for people to do what they actually want to do. So they not always want to just trade or provide liquidity, which are the only two things you want to do. In typical exchanges, you actually want to sell this much by this cost, this price, not by 1,000 more, not by a cent more. You have very specific preference, and these are, you want to express them. An order book is, in a sense, the biggest expression of preference you can possibly have, except if you start to add complex derivatives. Like, okay, I want to sell the right to buy a future Ether by this much USD, starting from this date, but ending on that date. If you start to add complex derivatives, then of course there is a way to express better your preference. But for immediate trades, an order book is is paradise. So that's why people don't get fully satisfied with Uniswap. Everyone wants a proper decentralized exchange. Now the problem is proper decentralized exchange scale badly, as stressed there. So here's where we're going to give a proposal, which I think is not scalable enough to be implemented on Ethereum right now in layer one. Of course, it could, but it would only be for the very, very wealthy. Like maybe Binance would be trading with other big exchanges like Coinbase. I don't know, through that thing. Maybe I don't know. But Binance and Coinbase, they probably don't want to engage with direct exchange with one another in a decentralized way. You can just log into the other and buy and sell. So I don't know if there would be a lot of requests for a decentralized exchange with an order book on Ethereum that was so expensive to trade on. But the system that I'm going to describe is efficient enough to run on layer 2. Actually, much better than the simple implementation I said before. So first, before explaining the data structure and everything, I have to talk a little bit about B+trees, which is a very classical data structure. Every programming language implements this and uses this sometimes most of the times as the standard library. So it's a tree everyone probably saw in computer science course, binary trees. They're very efficient for searching. So if you have ordered elements in the leaves here, and you have a pointer with the separation in each of these internal nodes, and you're looking for something, you can just say, hey, is it bigger or smaller than this one? It's bigger. Okay, so I'll go right. Smaller than this and bigger than this. Oh, I found it. So if you have n elements in total, you have a depth of log n. So very quickly you can find any element you're looking for. The problem with binary trees is that they're efficient for static data structure, because as soon as you will start to insert elements into it, it can lose this nice shape. So as I said, in an order book, you're going to have to insert things. So if you started with no orders and you start to insert, maybe you're going to insert the orders in the correct order, insert the asks in the correct order so that you get a nice tree like this. But if the price drops and people keep inserting it to the left, then you get something very inefficient. Now, if you're looking for something, you're going to have to hop here linearly until you find it. So it's very important that people get this nice shape all the time. And that's where B+trees come to play. They're self-balancing, meaning that no matter what you do in terms of inserting and adding, inserting and removing, they always keep that nice shape. They keep the elements sorted, and they allow for several different instructions. You can search as in the binary tree. You can access them sequentially, like the smallest, the second, the third, and so on. Insert and delete, everything in logarithmic time. Actually, sequential access, it's in constant time. So how does that work in practice? So it's not like a binary tree, because it has to have some wiggle room. So in this example I'm giving here, the root, every node actually can have 2 or 3 children. In general, the root can have a different number, but in this specific example, it's easy because everyone can have 2 or 3 elements. You see here, there are two children. Here there are 3, here there are 2. This guarantees the logarithmic search I mentioned, because as you go down in the depth of the tree, you at least double the amount of elements. So if you had n elements, at most you're gonna need log n in the base 2 to access each of them. Also, the keys are always sorted like this. But then the question arises, like, how do you insert or remove elements while keeping this constraint? Because if you delete this constraint, you lose the optimality. So, there is a way to do it. I'll briefly explain how it works. Can you read this small? So assume yes. So here you have one tree. So here you have one tree, and I want to insert the number 20 on it. So I'm going to first search. So 20 is bigger than 16, so I should search here. 20 is between 16 and 25. So you see there's actually wiggle room here. I can move this 25 to the right and put the 20 here. So that's what's done in this second representation of the tree. The rest remains the same, but the 20 came between the 16 and the 25. Now let's say I want to insert a 13. So I search for it, it's between 9 and 16, so that's this arrow here. Oh, the 13, sorry, I should be looking the tree above, the one we still have. So 13 is below 16, so I should move to this arrow, and it's above all of them. So I don't have wiggle room to add it, otherwise I'll get 4 numbers instead of 3, and 4 is forbidden. So this node is exploding, and I'm going to split it into 2. 2 elements go to the left, 2 elements go to the right. You see that as soon as it doesn't fit, I have 4 elements, which is equal to 2 plus 2, which is the minimum. So I can split without violating the minimum requirement of having at least 2. So now I have this 1, 4, 9, and 13 in 2 nodes, 1, 4, and 9, and 13. But now you see the 1, 4 was already here. But this new node that I created, it had to be inserted above. So I go to the 16 and say, I want to insert a full node to you that has 9 and 13. Okay, so I should insert it in between. And it's here inserted in between. So not only you can, that's very important for today, not only you can insert leaves, like here I'm inserting the 20, which is a leaf. I'm inserting the 13, which is a leaf. But I can also insert a full node or a full tree if I want. Let's say I want to insert another tree that looks exactly like this one, but with different numbers. And this tree is to the left of here, right? It's -1, -20, -64, 54, whatever. So I want to insert this whole tree here. What do I do? Okay, this one is in the same height, so I cannot do it. I'll create a new root and link to the 2. So after you think a bit more about it, you'll see that it's always possible to insert an element or actually a subtree to this thing without violating the 2-3 condition, the condition that everyone has at most 3. So here in the last example, you see a huge, so inserting 12 in this tree here, and you see a huge pop-up. Look, the 12 should be this node, but it doesn't fit, so this node splits into this 2. So now I'm inserting this guy into the parent here, but this parent is full, so it splits into 2. And now I create a new root to host the 2 subtrees. But everything is always logarithmic in the number of elements I have. So this is fine. I know it was fast. Usually this takes at least one day in a lecture, one full lecture to explain. So I'm going too fast because I'm talking about other things. So removing also, you have to worry about the possibility that a node becomes too small and it's not allowed. Here you delete 13. So you see this is not allowed because it would stay alone. So you have to remove this node from this guy, but it's not allowed because this guy has only 2. So if it remove one, it would have only one. So I have to remove this guy from this guy. But okay, it's not allowed because it only has two. So you create a new root. You use this guy as a new root, or you borrow someone from here. It's always possible to fix stuff, and it gets complicated sometimes. Okay. So what I wanted to say about decentralized exchanges that involve the B-tree in such a detailed way. So it's a way to represent order books, the same order books as we saw before, with B-trees as before, but we are going to add a little bit more information on the B-tree, and we are going to make orders, new bids and new asks much faster. So we're not going to loop through things, iterating and spending time there. So what do we do? Again, every bid or ask has an author, a price, and a quantity. That's just the same as before. You see that the bids are here. This is a bid to buy at price 1, 7 units of the thing. Here it's a bid to buy 11 at price 11, 1 unit, and so on. All the bids are here at leaves. And I add another information at each leaf, which is the accumulated sum of the volumes, of the quantities. So here, someone wanted to buy 7 units. Here, someone wanted to buy 18. So we put here the 7 and here the 15. That's the sum of 7 and 8. And here, someone wants to buy 3. So I add 15 to 3, I get 18. So I'm cheating a little bit because if I wanted to keep this accumulated sum at the leaves as it's indicated in this picture, if I remove the 4 here, if I remove this element with this quantity, I would have to update all these accumulated values here. And that would be linear. So I'd have to loop through all these, and that would be terrible. But believe me, there is a way to essentially get this without having to store them in the leaves. And the way you do it is for each node, not only you store the divisor, like prices below 13 are here and above 13 are here, you also store the total accumulated quantity to the left and to the right. So by storing those at the parent node, you basically can recover these numbers in logarithmic time. It's almost like if they were in the leaves and you could read them easily. And if you make some insert here, or you remove this 12, you just go correcting the accumulated in all the ancestors. You go fixing, like I'm removing the 12 that actually is also 12 units. So I remove 12 from this edge, I remove 12 from this edge, and everything's fixed. So that's important. We're going to have to keep these accumulated quantities for every node. And now I will explain what happens when someone makes a bid, let's say in this tree. So I took a picture from the internet of a tree that was bigger than the one previously, but it has this weird thing that it uses they didn't want to spread the picture too much horizontally. So these are leaves. These are the same at height as this. But, they store it like this to compress things. So there's only 3 levels: root, these intermediate nodes, and these are leaves at the same height, this and this. Okay, so I added here the volumes, which were not in the original picture. So this bid to buy at cost 11 is also to buy 11 units. This bid to buy 17 is 1 unit only. And here I added the accumulated, this accumulated sum of the above. So now let's see what happens when someone wants to buy 120 units at the cost of 35. So what we could do before is go removing all these things until we store 120, which is here, and make this linear arrangement here, which is not very efficient. What I propose here instead is the following. We have 120 units we want to sell. So we first find this 120, looking for the accumulated things in the arrows. And I find it that it's here. Sorry, it's here. So actually, I want to sell everything to the left here. And remember that in B+trees, I can remove a node and all its children very easily with logarithmic cost. So I remove all this tree and rearrange the rest so that maybe this only had 2 children, so I could not remove one, otherwise I would violate the principle of having at least 2 children. But this is what the trees are for. You can remove a node and rebalance the rest very cheaply. So I remove this whole tree and I say, okay, this is what you did. You sold this whole tree. Congratulations. And I keep working with the rest. I didn't tell you what I do exactly with the tree that I detached. I'm gonna explain later, but it's easy to detach this tree. It gets a bit more complicated if you are, let's say, buying 300 at 47. So now you look at 47, which is here, and you see that you don't have 300 to sell at this point. We only have 208. So you're going to remove this tree, which is a whole tree here. Actually, it ends at 120 as before we saw. Then you also remove this tree. Sorry, this tree here, this node here, you remove it because it's below. And then you remove a little bit of this node, and you're done. And you still have 92 left that you want to buy. Add this buy order to the other tree, the tree that has the bids. Okay, so it's always possible to do this. Sometimes you have to remove a few trees, but never more than logarithmic. And that's the problem. I didn't tell you what we do with a tree that we removed. Let's say we want, like before, we wanted to buy 120 and we bought this, and this tree is detached. What happens? So this tree that is detached, let's imagine this is a tree that's detached. It has this information, 120 at 35. So this becomes kind of an airdrop. Everyone that had a bid here, all the bids have an offer. So everyone who has a bid here can go and take a little bit of this money, which is associated to this tree. But this is very important. It's not, so the person who placed the bid that generated this tree to be shopped out is not responsible for distributing the funds. So for example, let's imagine that 1 million people make a bid of one way at the same price. Almost sounds like an attack, right? So million bids at the same price for very tiny amounts. So this tree is huge. And I want to buy this whole tree because I want to penetrate deeper into the costs where I can find more volume. Because this doesn't have any volume for me. I want to get rid of this tree and go find more interesting offers to the right. So I just detach it, and everyone who had this one-way volume bids here, they will have to make an operation to withdraw their money and subtract one way from this 120 times 10 to the 18 bids that I did. So you see, the huge advantage of this is that you're putting the effort in the hands of the people who created the task. And that's also a disadvantage. So let's review what we gain by this. I'm pretty sure people have questions by now, no? Don't you want to ask anything? Maybe it became too technical, maybe the connection dropped.
We've been reacting with emojis actually, but I just not realized that you cannot see.
Okay.
So you were not ignored.
Thanks. So what are the advantages and disadvantages of this? No matter what you do in this system, you have accumulated lots of bids and asks that are not paired. Whatever operation you do, adding another bid or adding another ask, is only going to cost you log square of the total you have already. So this is usually very fine. Although this is fine for Cartesi or for a DApps specific rollups, but it's definitely not fine for layer 1 or for a layer 2 that's not DApp specific, because this starts to add up, I mean, a reasonable amount. So you're sure that there are no attacks on this system, and I would say it scales well enough that you can have in a single DApp all the pairs. So you can have even people create new pairs dynamically, right? So someone says, okay, I want to add a pair of, this weird liquidity token of Uniswap for this contract and Ether. So you can create a pair out of the blue. And this is quite nice because it's not something that you usually can do without making the scaling dangerous. And I would say the cost, even if you transact very fast, as fast as you can on layer 1, what layer 1 gives you in terms of scalability of data, I think you can still handle it in L2. Of course, it's more complex to implement. It's actually not crazy more complex. Because every implementation needs a B tree somewhere. But the problem is that the B trees that usually exist in standard libraries, they don't allow you to remove chunks of data. So if it allowed, it would actually be quite reasonable to implement. Also, they don't allow to add another accumulator on top of the accumulator you already have. So yeah, you have to implement the B tree, I think, from scratch. And also it's asynchronous. That's a UX problem. So
sorry, could you repeat this last part? Why would we need to implement B3 D3 from scratch?
Maybe not to re-implement, but I think you would have to either use some shenanigans from a Boost library, because the Boost library allows you to add many hooks to things. Like, whenever you remove a node, I want to update some, they have templated the thing to death. So maybe it's possible to use one of their templates to your advantage. But you see, there are two things that we have to do that are not usual in the standard libraries. One is to add another data to the tree, which is these accumulated things you see below here. I want to keep track of those, and these have to live in these nodes here. Maybe the B3 doesn't allow you to add this extra information. And the second thing you have to add is the possibility to remove whole chunks and keep the chunks as a separate entity. I had previously this chunk, which was the ask bid, the ask book, and I'll remove this chunk and it becomes kind of an airdrop that I have to store somewhere. But it's not our ask book anymore. It's a separate thing. Usually the standard libraries don't allow you to do this. Or maybe I'm wrong. And another disadvantage comes from the synchronicity of the whole thing. So for example, if I'm not doing any attack, I'm just a normal user, I want to buy 1 Ether for $2,000. I put the bid there, and then someone actually sells it to me. The money is not on my account immediately. I have to go there and make a transaction to remove myself from the tree, and then I'll have the money in my account. Of course, this streaming could be done before the next transaction you do, right? So now I want to withdraw that Ether. I know they already bought it, so I can remove it from the tree and withdraw it in the same transaction. But this is something that has to be optimized for. It's more code if you want to join those. Yes?
So just so I can understand, this trimming, the reason it's not done, it could be done automatically, right? But you don't want to incur the cost of it to somebody else. You want to incur the cost of it for the withdrawer, something like this?
Yeah, I don't want to, because if someone, so let's go back to the example. I want to buy 1 Ether by $2,000. And I enter there together with lots and lots of people who want the same thing. And then maybe Binance comes and say, okay, here is a lot of Ether for all you guys. Give me your dollars. I don't want Binance to have to go through a loop, Binance's transaction to induce a loop that goes paying everyone. I want Binance to remove the tree, and now there is a tree somewhere like this that has 125 Ether in it, and everyone who had the bid can withdraw from this. So I will have to say, okay, I have one of these Ether here because you see my transaction here. I paid for 1 Ether here at this price, so give it to me. So we remove this node from the airdrop tree. After everyone operates, this tree doesn't exist anymore, but it could linger forever if someone doesn't react. So there was a question here. Yeah, I don't know if that was a while ago, but I agree with Diego that it's not a big deal. Oh, Milton raised his hand, please.
I'm also confused about the synchronicity thing. If I get it from what you said, you're talking about withdrawing from the rollup, because if you're just staying inside the rollup, there's no synchronicity, right? There's it's not a problem that Binance's transaction generated several transfers for all the user balances within the rollup, right? That's not an issue.
Yeah. So let's imagine.
So you have your balance. Everybody will have his balance. You'll get his money inside the layer 2 wallet. And then if they want to withdraw it, they can withdraw it or whatever. But the operation is synchronous in itself, right?
So let me agree with you with more details. So you enter the system with only US dollars, right? And then you made this bid. I want to buy 1 Ether with $2,000. And it stays there in the tree together with lots of other bids.
What do you mean by enter the system?
Like you enter the rollups. You deposited from L1 to the rollups a lot of USD or USDT. So now you are inside the rollups, and in your balance inside the rollups, there is a lot of stable coins.
Okay, but in practical terms, you did two operations, right? And you deposited some money on the rollup, and then you instructed a bid there. Exactly. There are two separate operations. If your exchange was like several pairs inside the same rollup, you could just keep moving around. You don't need to deposit dollars every time, right? You can just buy and sell.
So I will go through the whole process in my explanation. So you first deposit $5,000. It's there inside the rollups, but it's not in any bid or anything. Then you make this bid to buy 1 Ether by $2,000. It gets here inserted inside a big tree, and then Binance or some other big player sells lots of Ether to everyone here inside this chunk. So now you have in your account $18,000 that you didn't spend yet, and the 2,000 they are locked inside. They went to Binance actually, your 2,000 when they did this chopping, and you know that you have an Ether here, but it's not like you have a hash table that says you have this much US dollar, but in the hash table you have 0 Ether. But your client or your front end knows that you have 1 Ether somewhere. So it could actually show like 1 Ether here.
Why do you say that you have 0 Ether?
In the hash table of your balances, like inside the, as I said, you have balances.
Yeah, and on the layer 2, in the rollup, right?
Yeah, in the rollups you have a balance that is associated to each address.
Mm-hmm.
I don't know how to spell address anymore. And token.
Mm-hmm. Asset, whatever. Yeah. You have Ether balance, you have ERC20 balances, ERC1021 balances, whatever.
Exactly. And when Binance buys this chunk, sells to this chunk of people here, I don't want to look through this balance spreadsheet here. Don't want to go through all of them and update their balances.
Why not?
Because I don't want to do a loop.
Why not?
Because there may be 1 billion orders here to buy 10 to the minus 10 Ether.
Oh.
So I don't want to have a cost that is linear. I don't want to do the loops because I don't want the cost to be linear. So Binance just chops this thing up, gets the money, which is locked inside the book. And now people can withdraw from the tree. They can remove this from the tree and update their balances with an operation.
But that operation would be linear for them?
That would be linear, but it's the cost is incurred by the person who is actually ordering this to happen.
I don't see that. Are you saying that we have metering inside Cartesi now?
No, so can I say something real quick?
Yeah, sure.
So in aggregate, everybody who wants to withdraw would pay perhaps even more than what you would do if you were distributing the funds directly, right? But you don't necessarily care about that, right? Because each one is paying for the cost of their own withdrawal. Does that make sense, Milton?
Not at all. I'm very confused.
So you have, assume that you have only one of those trees, right? Those trees are, the tree captures all the things that people can withdraw. Anybody who can withdraw is in this tree. And so when they say, okay, now I want to withdraw. And so they're gonna send an input to the machine and they will withdraw. And then the next person will send an input to the machine and they withdraw their own. And then another person, each person is doing one withdrawal. There'll be 1 million withdrawals, sure, right? But each person paid for their own withdrawal. And each individual withdrawal is very efficient to run. Does that make sense?
Yeah.
So it's not the case that there will be one input that, and in fact, the input of the person who wants to sell, right?
Yeah, I'm confused because you're always associating selling with withdrawing, and I don't see that.
Yeah. You don't need to withdraw. Let's say, for example, that now you want to sell Ether to another coin, like
exactly.
I don't know. So you cannot do it directly because you have 0 Ether in your balance variable. But what you can do is you send the transaction. It could be the same transaction, by the way, that chops your bid here. So it sees that, oh, indeed, you are one of the persons who gave that money to Binance back then. So here is your Ether. So it's going to update your balance to 1. And now in the same transaction, you could actually put this in the order book of another pair, Ether or something. So you're basically passing to the person the burden of finalizing
stuff around. Yeah.
But
yeah.
I'm very confused still, because you talk as if doing this operation within a Cartesi rollup would imply some costs to the one who just asked for it, and I don't understand why.
But they
Because
sent the
there's no
input,
metering.
right? They sent the input.
No, but if you're doing more loops or less loops within the Cartesian machine, that doesn't imply more costs to the guy who sent the input, right?
No, but there is no metering, but there is this issue of the result of processing any single input can't take too long, right? So consider it like this.
Yeah.
Right? You don't want any input, processing of any input to take an unbounded amount of time, right? And so now you get this. So you have this property.
Okay, but still, if the one guy just sent 1 billion one-way things, when he decides that he wants to withdraw or to transfer or buy something else, you have to look through it anyway.
But he'll have to but then he'll have to do it himself, right? What we don't want is two properties, I guess, that in the case of Cartesi, the two properties. One is we don't want the processing of any input to take an unbounded amount of time, and in particular, we don't want the poor guy who just is selling, right? They didn't know that there was a billion buyers for the stupid tiny price.
Right.
It's really not his fault, right?
Yeah, so I guess that's the thing that I get. So we want to avoid like side effects. So if you are not doing something crazy, you won't get crazy, lengthy process.
Yeah, it's but not your thing that is going
happen,
to be reported, right?
Yeah, but it still can happen that the thing freezes and reverts or something weird happens. But then it happened, and the guy who sent the input, he knows.
Freeze. No, he can't freeze.
But it will revert if it takes too long, whatever.
No, but it can't freeze, right? In this situation, nobody can freeze. Nothing can freeze.
One way to freeze the system is if you can send so much data availability in L1, like so many, if so many bids in L1, only the data, right? But you can send so many bids that the system cannot process them.
Yeah, but that's not what we're talking about. Well, they're going to be independent. They're going to be independent things, right? This is all assumed that you can process a bunch of bidding and withdrawals, and there's a certain number that you can, and that fits in your computational budget associated with a certain amount of data that you can process, right? So that is a given.
And then you enter an interesting aspect, which is, okay, one can implement this without any type of metering and just let the system evolve in the assumption
so there's one detail that I'm confused about. I was trying to explain something to Milton, but also selfishly because there's something I don't understand, which is you can have a bunch of these trees, right? Thousands of these trees. Yeah. So the trees that are let's call them airdrop trees. You can have thousands of them. And so you need to be able to check each one of them when somebody wants to withdraw. So there has to be a data structure of airdrop trees there. And you don't want...
But this could live outside. This could, the person in the front end, by looking at the events, they say, okay, I want to withdraw from airdrop tree number 5,426, and here's my node there.
Yeah. It's just this detail that you have to have this management of the trees also be outsourced, right? In a sense.
And by the way, it could very well be that before removing the tree, you check, and if the tree has less than 20 nodes, you do it yourself, you loop it, you know? And if it has more than 20, detach.
No, but I'm just thinking about an attack, right? Which is somebody makes a bunch of these trees, and now nobody can withdraw because you can't find the trees, right?
So your money is only fractured or pulverized by your own doings, right?
Yeah.
You had to make several bids in several different things to get your money pulverized like that. But if it's only 20, it's fine. You can send one transaction that has 20 numbers in it, and the rollups are gonna make everything for you. But now that's an interesting thing. What if that's the prediction, right? What if the price of data in L1 drops abruptly and drops so much that now you can clog the system by just making crazy one-way bids? So the attack becomes possible again. So that would be, if we have implemented this airdrop system here, it would be a great place to be, because we could just add a tiny bit of metering. Like every transaction costs one gas. So if you're doing anything, a bid or a withdrawal from an airdrop, you pay one gas. And there's a block size, and there's a bidding for, like, you have to pay for the gas. There is a system like Ethereum to avoid the block becoming full. There's a payment for gas, and that would completely solve the problem. Of course, now there is metering, and not everyone can send their bids for very cheap, even though layer 1 is charging very cheap. But now you have two costs. You have a layer 1 cost and a layer 2 cost. But if you didn't have this system, you would be charging the wrong person, right? The person who did this huge sell here, they would have to loop through these things and pay for the gas. Or said in another way, either you are making someone pay for the mistake of others, or you are getting an unpredictability. Like the person only did one transaction, should cost one gas, but you are making a huge loop that slows down the machine a lot. So with this system, you have a very good bijection between one transaction, this amount of time. So you can build a metering system later if needed. I just left some tiny observations for the end. So on top of all this, you can also add another Uniswap. So Uniswap, I didn't explain exactly how it works, but you can think of it as an order book where you don't get to specify all the prices and volumes. You just have two curves, one for asks, one for bids. It's like this. It's a continuous curve. And if you add more liquidity, you just increase the volume. And if you buy something, you just rearrange the curves in a way that they now give you the amount of money you asked for, charge you how much it has to charge so that the curve moves correctly. So the price is where these two curves meet, the left and the right curve. So this is the price at Uniswap. So you can look at Uniswap as kind of an order book that doesn't have a lot of flexibility like this. It just has two numbers. And if you look at it like this, you can add a Uniswap on top of that system with a bit of math. So that means you get all the advantage of Uniswap, like a market maker, a way for people to stake and make money and charge fees and so on. By the way, I don't think there's any obstruction to have all the pairs in a single DApp, and even people creating new pairs on demand. And a last thing that you could do, which is kind of strange, but why not, is allow people to make arbitrage matches. Like you bundle lots of matches in one. Like for example, in the pair Ether BUSD, I want to buy some Ether because I saw that there is a Ether to be bought. In the same transaction, I want to sell that Ether in another contract, and then I want to get BUSD again. So you do a triangle and you make money actually. And you're kind of reducing the inconsistencies of the model when you do this. So people could propose some triangle things that get the price closer to reality without the risk of losing money, because it's an atomic transaction. If it gets in, it's fully executed, or it's not, nothing is executed, then it's clearly making money. So you could even say, okay, if you find an arbitrage match, you get that money for free, and L2 get some fee. We guarantee you that you never lose money because it's atomic, but we charge you some fee. Okay, that's all. It was quite technical, Milton.
Just a quick question. You believe all pairs could remain in one DApp with the Uniswap approach or with an order book approach?
With that modified order book, I don't see why not. I mean, even with Uniswap.
No, Uniswap, of course, but you mean the one with the B tree that you were explaining, you believe it would fit into one rollup?
Yeah, the big question one has is like, why would you want to shard different pairs to different rollups? You could, right? And
yeah.
the big advantage of sharding would be that you don't overburden one of them with transactions from the other, right? There are one pair is not fighting the other for computational power. Mm-hmm. But I think with this approach, I mean, benchmarks are the only answer. But with this approach, it may be possible to put everything in a single universe.
A limit will happen at some point, right? If you have billions of people trading, sending inputs every second, at some point.
Yeah, so the question is, there are two important limits to keep in mind. One is the current maximum that L1 can send to L2, right? Because every transaction needs data availability in L1. Even if it compress and makes the most out of it, there's a cost for L1 to send data, and maybe the L1 saturates before our machine clogs in terms of computation. And then there's a second number, which is very important, is how much data L1 can send to L2 after EIP 4844 and sharding, which is going to be a lot more. Mm-hmm. So maybe benchmarks and some back of the envelope computations could answer this question and say, okay, no, even if we put, like imagine the following scenario, even after L1 makes all the updates, L1 cannot clog a machine that is with all the pairs together. Of course, it would be very optimistic to think that Ethereum is sending all its data availability to a single centralized exchange built now. But anyway, maybe it's possible to take this decision for him.
It can be aggregated, right? If it's a layer 3, etc. So.
Yeah, then you start to look, as soon as you start to look at alternative data availabilities, like committees, then the sky's the limit. Probably there will be an advantage in having one DApp with all the pairs for better composability, and maybe a few DApps with very important DApps that are exclusive, because they give less friction and can do high frequency trading or whatnot.
Cool.
Okay, sorry for the off topic. Yep.
So when you say like arbitrage matches and stuff, can you give me more details again about that? I think I missed the details.
It could be that you look at the books and you see the opportunity for a triangle that only makes you money,
Yeah. My question is there a design of this set of order books where there's no arbitrage like inside? Is that? Like, I don't know, if instead of being like all pairs, you know, like having, I don't know, like token 1, token 2, then token 2, token 3, 3 and 1. If you have something like a star, you know, like everything, you see what I mean?
It's very interesting.
Are there like designs where you don't have arbitrage at all, you know, or any arbitrage is like automatically fixed? I don't know.
Yeah, this
like
is very
always inside the DApp, right? No, not outside, just inside.
The only, I mean, this is very interesting. Instead of having a one-dimensional order book, if you have, say, 3 assets, you'd get a 2-dimensional order book. And the spread, maybe I can draw this, but it's kind of crazy. I don't know how useful that would be, but it's kind of imagine a triangle, and you have, you know, orders for one asset here, orders for another asset here, orders for another asset here. And these orders are like, I'm selling this, and I would accept any amount of the other 2 tokens in this proportion given by the slope of this line here. It's kind of...
Oh, that's crazy, yeah.
And then you get something like this. This is the spread.
Wow. Okay. Could you generalize that to n dimensions? You know? Yeah. Oh shit, that's cool. Yeah.
But now it's.
Yeah. You know, I was thinking. Yeah, I was thinking something simple like a star. You know, you cannot have any pair. You can only like launch a token X dynamically, but always like to the same base. I don't know, choose Ether or native token. I don't know. And then if you have Ether and you want like ET, then you have to do 2 swaps, you know?
Yeah, it's possible to join several pairs into a star, but you either need to do a lot of computation on the machine to guarantee there's no arbitrage, or you need help from outside, because it's a tough computation.
And if you need help from the outside, that essentially, yeah. But
it reminds me of the kidney. Reminds me of the kidney problem, right? In economics, that you might want to donate a kidney to a person that you care about, but your kidney is not compatible to the person. But then if you could only find somebody else who is compatible that needs your kidney, they have somebody do that, you know. It is actually a problem that happened and that was solved, and it's really cool. Like how they do now. They do these multiple matches that a lot of people go to surgery together, and then kidneys go all over the place. Yeah, because otherwise you can't close these orders, right? Of course, kidneys are not really fungible, so I don't know. Maybe there's something similar with NFTs that could happen.
That would be interesting to have. You know that NFTs, that's something that Max actually explained. The NFTs, they have of course, the clearly fungible NFTs, non-fungible NFTs, like you know, this very pricey board monkey. Or you could have, there are some kind of fungible NFTs. So it's like, imagine you have like 1,000 NFTs that are kind of in the same class. So they go to an order book. You know, I've seen, they have nice interfaces that look like an order book, and they trade this. It's centralized. But it's very cool. It looks like an order book where you're sweeping spooffuls of NFTs. They almost lie between fungible and non-fungible. But okay, I think that's it, but people actually do it. So you end up with 1,000 semi-rare monkeys.
Oh. Yeah. Just one last question. Do you think like this triangle was generalized to n vertices, whatever? Do you think that's like reasonable? Do you think that's cool? Do you think that's like, is there an application there or something?
Of what? What generalized?
The crazy triangle we just drew? Yeah. The generalized
I have a simple opinion on this, which is if this doesn't exist in the centralized world, like an actual, if this is not an instrument, a financial instrument, or a way to do trades that people do in the centralized world, and it's interesting, then we should do it in a centralized world and get rich that way, right? Because it's just much easier to do it in a centralized world, right? So
yeah,
No, but
that makes total sense. I tend to agree, but maybe the decentralized is what actually makes this feasible. I don't know.
yeah, I don't know. Yeah,
yeah,
maybe.
actually, there are two forces, right? In decentralized, you can experiment with much more. Like Uniswap did a crazy experiment that it's probably very hard to do. Okay, it was probably kind of stupid to do in the centralized world also, but it's possible to do experiments like lending liquidity tokens. But also in centralized contexts, you could do so much computation. They have these huge data centers that sometimes you can enforce this triangle here, a very weird opinion you have, or preference, they call it in economics. You can express a weird preference through lots of transactions. Just buy this tiny bit of this thing and buy a tiny bit of that thing and sell this tiny bit of that other thing, which is equivalent to this crazy triangle that you can do by just sending several orders. Okay, we have over time. Sorry for the technical subject. Eduardo posted, several people posted here. When you clean the airdrop list, when the tree is empty, then you can clean it. Yeah, you have to maintain a list of airdrop trees. Yeah, you can use, I think arbitrage can be used in very creative ways. Yeah, for the triangle, it would be weird to create an order, but not so much. What you have to do to create an order in the triangle is to price all the assets. Like, I think Ether is worth this many USD. I think CTSI is worth this many. This is worth this many. Then you place the order. And you're going to get some weird proportions that were respecting your opinion. But Eduardo's question is very interesting, because now the concept of ourselves is becoming very dissolved. We hope that the community does something like this, and we are the community. So maybe Felipe can answer better, but yeah, we hope that the community does it, and by community we mean us. But yeah, a framework could be because a DEX is a lot of work. Some of it is like a startup type of work, right? Find a good lawyer and whatnot. But the framework is something that is fully self-contained. It's just C++ code. And if we have a DEX, it could be the seed also of a much more powerful Cartesi network.
It also involves going over these. I'm talking to, I don't know if Pedro is the best person to do that, but there are lots of different types of orders that you can put. And we have to see if all those are compatible, which ones are, which ones aren't, and make sure that we support them.
Some may not be compatible, but can still be implemented in log square. So great, let's do those as well.
Yeah. So like stop loss orders, and I don't know the names. But you guys know better than I know, right? There's like a bunch of different types of ways you can place an order that triggers that specific with specific conditions.
Margin tradings are very
complex. There's a bunch. There's some like you don't want your order to close if you already can close, right? Because you want to make the price instead of take. There's all sorts of stuff.
Yeah. Great. Thanks a lot for the patience. See you next time. So next time there will be no research meeting, but there will be news.